Hello students, let us start with theorem. Let order pair xd and order pair yd2 here d1 be two metric spaces. Be two metric spaces. Be two metric spaces. A sequence order pair xn yn in the product metric space x cross y is a Cauchy sequence if and only if sequence xn and sequence yn are so in x and y respectively. Let us see proof of this theorem. We have given that xd1 and xd2 be any two metric spaces. A sequence order pair xn yn in the product metric space x cross y is a Cauchy sequence if and only sequence xn and sequence yn are so in x and y respectively. Means we have to show that sequence xn yn in the product metric space is Cauchy sequence if and only sequence xn and yn are Cauchy sequences in x and y respectively. Okay. Consider the product metric D from x cross y to R given by D of order pair x1, y1, order pair x2, y2 is equal to D1 of order pair x1, x2 plus D2 of order pair x2, y1, y2. Okay. For order pair x1, y1, order pair x2, y2 belongs to x cross y. Okay. Assume first that sequence order pair xn yn is a Cauchy sequence. It's a Cauchy sequence in x cross y, d. And our claim is sequence xn and sequence yn are Cauchy sequences in x and y respectively. Okay. Here use definition of Cauchy sequence. Therefore, for each epsilon greater than 0, there exists a positive integer. There exists a positive integer n such that there exists a positive integer n such that d of order pair xn comma yn comma order pair xn comma yn, because here our sequence is in the form of order pair, is strictly less than epsilon for all m comma n is greater than or equal to n. That implies here we have defined d is equals to d1 of x1 comma x2. So this is d of xn comma xn plus, here is d1 plus d2 of yn comma yn, since by this equation, okay, which is strictly less than epsilon for all m comma n is greater than or equal to capital N. That implies, see here, addition of these two is strictly less than epsilon, so each number, so d1 of xn comma xn is strictly less than epsilon and d2 of yn comma yn is also strictly less than epsilon for all m comma n is greater than or equal to capital N. That implies sequence xn and sequence yn are Cauchy sequences in x and y respectively. Hence we have proof which we want to prove. Now we will prove converse part. Okay. Conversely, we have to assume that sequence xn and sequence yn are Cauchy sequences in x and y respectively. Conversely, assume that sequence xn and sequence yn are Cauchy sequences in x and y respectively. And our claim is sequence order pair xn yn is Cauchy sequence in x cross y. Okay. Therefore, for each epsilon greater than 0, there exists a positive integer n1 and n2 such that d1 of xn comma xn strictly less than epsilon by 2 for all m comma n is greater than or equal to n1. And sequence yn is also Cauchy sequence in y. So by definition, d2 of yn comma yn is strictly less than epsilon by 2 for all m comma n is greater than or equal to n2. Okay. So choose n is equal to maximum of n1 comma n2. Okay. Now d of xn comma ym comma xn comma yn is equal to what? d1 of x1 comma x2, here is d of xn comma xn plus d2 of ym comma yn. But here we have chosen n is equals to maximum of n1 n2. So here n1 and n2 will be replaced by n, and this is d1 of xn comma xn is strictly less than epsilon by 2 plus epsilon by 2, which is equals to epsilon for all m comma n is greater than or equal to n2, and therefore we get d of xn comma ym comma xn comma yn is strictly less than epsilon. That implies sequence order pair xn comma yn is a Cauchy sequence. Okay. Here is for all m comma n is greater than or equal to n2. Okay. I hope all of you understand the proof of theorem. Let us write down definition. First definition is of constant sequence. Let XD be a metric space. Let XD be a metric space and sequence xn be a sequence in capital X. If xn is equals to x for all n belongs to set of all natural numbers, then sequence xn is a constant sequence. That means all terms of the sequence maps to a constant number. For example, if you consider sequence xn is equals to sequence 1, n runs from 1 to infinity. Here also n runs from 1 to infinity. This sequence is 1, 1 and so on up to. Here your xn is equals to 1. This is a constant sequence. Okay. Next definition is eventually constant sequence. Okay. Let order pair xt be a metric space. Let order pair xd be a metric space and sequence xn be a sequence in X if xn is equals to if there exists a positive integer, n0 such that xn is equals to x for all n is greater than n0, then sequence xn is called a eventually constant sequence. If there exists a positive integer n0 such that xn is equals to x for all n is greater than n0. Then that sequence xn is called eventually constant sequence. Okay, we will stop here. Thank you.